Hey, how you doing? My name's Eldon. Welcome to Learn Docker in a Month of Lunches. This is episode 12. We're continuing our journey with orchestration, looking at Docker Swarm, but highlighting all those same facets of orchestration that you'll work with if you're looking at Kubernetes or another orchestrator. And today we are looking at distributed applications and the kind of application modeling language that you use in Swarm, which is an extension of the Docker Compose format. So when you deploy an application to Swarm mode, you create this thing called a stack, which is a combination of services, and today we're going to be looking at deploying your application as stacks and modeling it in YAML. Okay, so let's have a look at the slides for today. So if you're new to the series, then we always start with a look at the website to see what's happening, which is usually not much, just a new line in the links to all the episodes. Today's focus is actually chapter 13 of the book. So this is deploying distributed apps as stacks in Docker Swarm. And then, as always, Q&A at the end. So if you've got any questions, put them in the YouTube chat channel, put them in the Slack channel for DIAMOL, and I'll pick them up. And if there's anything worth talking about at the end, usually kind of talk for 50-ish minutes. And then if there's topics at the end to go through, I'll pick up your questions then. Okay, so let's crack on. So it's going to switch to the website. Let's do this. So I was going through my demos earlier, so that's why you can see that error screen. So this is the kind of homepage for the book. It's published by Manning. You can get it on Manning or Amazon. Manning website. They've usually got loads of really good deals. So head there. If there isn't a deal at the time you're watching this, you can use this code to get a discount of 40% for the digital or the physical copy of the book. There's a whole bunch of other things around the book. So there's obviously this live stream, which is the serialization of the book. That short link will always take you to the latest episode. There's some giveaways that I'm running. I'm running them while I'm doing the series live, but also I have regular things to give away. So have a look there. So you might win yourself a copy. And there's the Slack channel. I'm kind of hanging out there. So if you've got any questions when I'm not online, then not live, then you can put them in Slack to me there. The sequel to this book is called Learn Kubernetes in a Month of Lunches. Really, the reason for writing these two books is that a lot of people are super interested in these technologies, but they just kind of pick pieces up. So they'll get a Docker file from Stack Overflow, and they'll get a Kubernetes YAML file from a blog somewhere, and they'll kind of fumble along and try and get things working. And you might get to something that looks okay, but unless you understand the principles and the kind of the core practices around this stuff, it'll all fall apart badly sooner or later, and you won't really know how to start picking the pieces back up. So these are kind of first principles for containers are in this Learn Docker book. We talk about orchestration, we talk about some of the practices, some of the management practices like monitoring that we've covered. And the sequel is all about Kubernetes, which is probably how you will run your containers in production if you're looking at a cloud platform. Okay, and there's a whole bunch of links down here. So these are all the episodes that I've done so far. Haven't I been busy? Thank you for joining me if you've been along for the whole journey. And today we're on episode 12. There's a playlist there. If you want to know more about me, there's a little pitch. And the rest of the stuff I do, mostly it's on Pluralsight. So if you've got a Pluralsight subscription, you can watch my courses about Istio and SRE and Kubernetes and Docker and Azure and all sorts of stuff. If you don't have Pluralsight, then ping me a DM in Slack, and I can send you a 1 month. I think I've got a bunch of 1 month free codes. Okay, cool. So I think that's about as much advertising as I can stomach. So let's get on with the episode. So here we are in Visual Studio Code. So this is the book. So chapter 13, deploying distributed apps as stacks in Docker Swarm. So if you're following along with the series, then in the last episode, or if you're reading the book in the last chapter, I introduced the concepts of orchestration, and we used Docker Swarm, which is the orchestrator that's built right into Docker. And we did some kind of basic imperative work. We did Docker service create commands to start these services running so that we can explore them and look at them without getting too bogged down in the modeling concepts. But the reality is, as it says here, like you don't really do that. So you don't typically do a Docker service create because that's not how these things work. If you're using your orchestrator, you will have your application modeled in a YAML file that describes the desired state rather than going and kind of hacking and creating things on the command line. Don't particularly like to teach things that you won't do, but it's a really good way to get started and get introduced with the concepts before we kind of dig a bit deeper. And we're digging deeper today. So the YAML file that you'll use for Docker Swarm is effectively the compose specification. It's that same kind of desired state approach. So here's my application modeled in YAML. Here are all the pieces that fit together. You throw that to the orchestrator, and then it goes and distributes the work around the cluster. And again, there are all these different layers of abstractions. There's a networking layer, which makes it simple to connect containers wherever they're running, which also takes care of ingress, which is getting external traffic into your cluster and sending it to your application. There's the storage abstraction, which deals with volumes and storing state across the cluster. Then obviously there's the runtime abstraction, which is the containers themselves. It's all modeled in that YAML file. And we'll see a bunch of that stuff today. Okay, so I've talked a little bit about how these things compare. Kubernetes is massively more configurable. It has a way bigger feature set. It's more complex, but if you need some of the things that Kubernetes does, there's stuff that Docker Swarm just doesn't do. But the corollary of that is Docker Swarm is much simpler. It's easier to get started with. The application models are much smaller and kind of more succinct and easier to read. So it's easier to kind of get up and running with, especially if you're just starting out in this stuff. You've got an eye to Kubernetes in the future, but learning a simple orchestrator will get you a good way along the way. Okay, so the way compose works is that you have the same kind of core specification. So this is a perfectly good compose file that you can deploy to Docker Swarm. So I could, on a single machine, I could take that YAML file and I could do a Docker compose up, and it will start a single container from that to-do list application that you've seen before if you're a regular viewer. And I can take that exact same file and I can deploy it as a stack in Docker Swarm. So I will still get kind of fundamentally the same thing. The app is available on port 8080. But when I'm deploying across the Swarm, of course, I've got all the failover, the reliability, the ability to scale, the distributed networking to load balance all the requests across a bunch of containers, across a bunch of machines. I've got all that stuff without adding anything to my compose file. But of course, there are some things that are only relevant when you're working in a cluster. And you can add more to the compose file, and the deployment is smart. So compose, there are some things that only apply when you're using compose. So if there are swarm relevant configurations in your YAML file, compose will ignore them. There are some things that are only relevant to swarm mode, so compose ignores them. There are some things only relevant to compose, so swarm mode ignores them. I think you just said the same thing over. We get the idea. They only apply the bits that they care about. Okay, so in this chapter, we've got a whole bunch of exercises that basically start with a nice simple YAML file. Start with a really simple definition, that same definition for my to-do list application, and gradually layer on more and more features of the orchestrator by extending that YAML file. So you'll see down here, there are configs and secrets that we'll come to. There are a bunch of different versions of the application. We're gradually kind of exposing more and more features of Swarm mode. So by the end of this episode, you'll have an idea of how all those networking and storage and runtime abstractions kind of fit in. Okay, so let's close this down, open up my terminal. So I'm already in, I think I'm already in the right, I'm in the right place here. I'm still in swarm mode from the previous time I did those exercises for yesterday. Easy way to check if you're in swarm mode is just to be running docker info. That prints out a whole bunch. It's one of the few commands that doesn't produce JSON output, so you can't easily automate it. But it's a nice kind of text readable output. It gives you a whole bunch of information, including whether you're in swarm mode, and if you are in swarm mode, a whole bunch of information about the swarm setup. So I'm already in swarm mode, but I've got nothing running so far. So if I look at my services, I haven't got any. And if I look, because I'm connected to the machine, which is my my node, if I do a docker container ls, then I've got nothing running. Okay, cool. So I'm going to do a Docker stack deploy. So this is how you take your YAML file and you deploy it to the cluster, and you get and remember, it's the cluster that runs containers for you. You're not going to connect and individually run containers. That's the job of the cluster. The equivalent here in Kubernetes is a kubectl apply command. But the YAML file for Kubernetes to describe this, you'd probably have at least two YAML files describing two different objects, which when you deploy them will actually create four different objects. So there's extra layers in Kubernetes. Okay, so let's do my stack deploy. This is the version 1 YAML file that I've just created. It's creating a network to connect all my service containers together, my service replicas, and the service itself. Okay, so that all looks good. If I go and look at my stacks, the stack is a first-class citizen. So this is one difference between Swarm and Kubernetes. Swarm takes this notion that your compose file describes an application which is made up of many different services that all kind of connect together. So my front-end website, a bunch of APIs in the back end, a message handler, a message queue, a database, all those things are in my compose file, or multiple compose files with overrides that we've learned about in the series so far. And you describe them as a single stack. So I've got my to-do application is one stack that's composed of, in this case, one service, but it could be multiple. Kubernetes doesn't really have that abstraction. So in Kubernetes, you've just got a whole bunch of things which you have to know relate to a single application. So the stack is a way to kind of clarify that that Docker Swarm uses. So I've got my single stack. If I look at all my services that are running, I've got my single service. So it's my to-do web application. It's running from my to-do list container image. And I've got 1 out of 1 container, 1 out of 1 replicas running, so a single container, and I've got my port published. Now, I'm in Linux container mode, so I can go and browse to that application. If you remember, there's a limitation in Windows on swarm mode when you're running locally. You can't use localhost to browse. Um, Typically, if you're working with Windows containers and you're using Docker Swarm, your swarms will be your non-production environment, so they'll be a remote environment anyway. I could use a different machine and connect to it, and everything just works. It's the localhost bit that doesn't work. Okay, so here's my application. It works in the same way that it always did. So let me do my finish episode 12. I store that. Stored currently this application, storing the data in a SQL-like database inside the container. Obviously not production grade, but we'll evolve that as the episode goes on. So everything works. It's running in Swarm mode. It's running as a stack, which is described in that really simple compose file. I didn't have to do anything smart to get production grade orchestration for my application. Okay, so let's close this down and see what we've got coming next. Wait, there we go. Okay, so you see my output in here. So I've got all these stuff here. You've seen I don't take a screenshot of the to-do list app every time because the book would be twice the size. It's the same thing. It works in the same way, but now I've got high availability. So I could add another node to my cluster, and I could scale up my to-do list web service, and I would have multiple instances running, and they would all be able to share the load that came in. And if a node died, then the swarm would start up replacement containers on different nodes. So I've got the high availability, but I haven't had to remodel my application. Like if I'm already using Docker Compose for the build stage, then I've got that kind of core definition that I've talked about, and then the override files. That's already kind of the basis of what I need to deploy to production. Okay, but of course, Swarm has extra features because it's an orchestrator and it can do interesting other things. And so you can add to that compose file and set configuration settings that only apply in Swarm mode. And so this deploy stanza, which we've got here, this is the new part of this v2 YAML file. This has got my replica statement. So I'm saying I want to have 2 instances of my web application now, and it's also got these resources. Let me switch to the real YAML file, and you'll see this a bit better. Okay, so the first part is the same. So I've got my service definition with the ports and the image, and that's all exactly the same. I've added this part here, the deployment part. This will only get used when I do a Docker stack deploy. If I do Docker compose up, I will see a message saying there is a deployment stanza in here, which I'm going to ignore because that only applies in Swarm mode. So in Swarm mode, I get 2 replicas. If I run as Docker compose, I only get 1 because this gets ignored. And I'm also specifying these resource limits. So this is something that Kubernetes has as well, and the other orchestrators. When you're running your containers in production, you want to be able to kind of put hard limits on how much compute they can use, so they don't kind of go rogue, or if a container gets compromised, some malefactor could be just jamming up the CPU, hoping that it would knock out all the other containers and take your server offline. If you've got these hard limits, then that won't happen. So each container will be restricted to half a CPU and 100 meg of memory. So quite a kind of narrow constriction, and they can't go above that. That's all the container sees when it starts up. It thinks it's on a machine with half a CPU and 100 meg of RAM. So if it tries to max out the CPU, it can, but it's only maxing out half a CPU on the physical machine where it's running, or the VM where it's running. Okay, so those are things you kind of need in production. So you should be having those things, but in non-production environments, you don't use those. So that's why I've never introduced those up until now, because in your non-prod environments, you want as much density as possible. So unless you're creating a production-like environment to verify all these resource restrictions, you don't want to put limits in, because that harms your ability to cram as many containers as possible in your non-production environments, and that's exactly what you do want to do. So this comes in kind of production and NFR environments, and production testing environments. Okay, so this is the limits that I'm putting in here. So when I do my stack deploy, I just do effectively the same command. I'm using a new YAML file here. Let me go and do this. So it's my version 2 YAML file. Typically, of course, it would be the same YAML file, but with different contents because it's evolved over time. So imagine that I've got my GitHub repo. I've just done a pull, I've done a deploy, and then in my next version, I'm doing a pull to get the next version of the YAML file, and I do a Docker stack deploy. The output I get tells me it's updating the service, so there's only one thing in there. And if I do my Docker service PS now, what I will see is my previous one has been stopped. So my previous container, my replica, has been shut down 5 seconds ago, and I've got 2 new containers. So one has been running for 8 seconds, and one has been running for 4 seconds. So you can kind of see the approach that Swarm took there. It started the new container first, the one that's been running for 8 seconds. When it was happy that was up and running and the process in the container was stable, then it killed the previous container and then it started up the second container. So this is the kind of gradual rollout that I talked about in the previous episode. This is how it looks when I'm running at scale. So I get that kind of safe rolling upgrade, and I don't lose service while the update is happening. Okay, so I can see the updates that are happening there. Typically, your Docker container will access all the CPU and memory unless you specify a limit, but that's why you specify these limits. If I go and look, because I am on the machine that is running these containers, if I haven't done that before, Docker PS is just a shorthand way of doing Docker container ls. It's just lists all my containers. If I go and look at the details of this one, so I'll do a Docker container inspect. I didn't get any spellings wrong there. This is my Docker container inspect. Piles out a whole ton of JSON, and way up here, way up here, I can see those limitations that I've put in. So my memory is specified in bytes, so that's 100 megabytes as bytes. The nano CPUs is the number of nano CPUs that are allocated to it. This kind of fictitious allocation of CPU that Docker uses. Kubernetes has a different fictitious allocation of CPU. This is like 5 million nano CPUs. It equates to half a CPU. Okay, so I can see that those restrictions and inside the container, if I push this container out to the max and then looked at my task manager on my Windows machine, I wouldn't see my CPU being maxed. Only one half of one CPU can be used by that container. Okay, so we've seen that next definition, which is all kind of nice and simple. So I didn't need to do anything. I had my new YAML file, I did my Docker stack deploy, and then Docker Swarm did the desired state business. So it looked at the service that was currently running. It looked at the definition of it and it saw two changes. So we'll see. I think there's some words around here before I get ahead of myself. Perhaps not. So there are two changes. Firstly, number of replicas. So it's going to add another replica, and then the resource limits. Now those resource limits are part of the container environment that are created when the container is created. You can't change those. So just like I can't open my machine and stick in an extra CPU, you can't do that with a container either. If you change the amount of memory it has or the CPU limits it has, that's a new container. So this is something you kind of need to get used to. A lot of the updates that you do in production, and it's the same with any orchestrator, effectively mean you're going to tear down an existing container and replace it with a new one. So you have to be comfortable that your application can deal with a kind of graceful shutdown. If it's got active connections from people using it, then it needs to be able to gracefully drain that connection pool, deal with all those requests, and then come back to the container platform and say I'm done. And then that container gets killed and the replacement comes up somewhere else because of its new configuration or a new application setting or a new image or whatever. Whatever the workflow is, the end result is the same. You're gonna have a container that gets killed and replaced, and you need to be confident that that won't cause any problems with the application. Okay, so stacks are your management unit. So if I look at my Docker stack services, it will show me all the services in my to-do list application. So there's my single to-do web. It shows me the image. It shows me the number of replicas and the ports that are published. That 2 out of 2, as I'm sure I've said before, the desired number is 2 and the active number is 2. If I had a failing replica, it would say 1 out of 2 until it had started a replacement, then it'd be back to 2 out of 2. So I can go one level deeper and I can look at all the containers. So Docker stack PS is going to show me all the containers for all the services in that stack. There's only one in this case, but it shows me the kind of historical container evolution as well. So I've got my current to do web.1, to do web.2, and then the one that was shut down because the existing definition didn't have any CPU or memory limits. So it didn't fit my new deployment, so it got replaced. Okay, and because the stack is the whole thing, I can do a Docker stack RM, and it's just going to remove the services, removes the network, removes the containers. Everything's gone now. And it's the same whether that YAML definition had like a single service in there or a dozen different services with different networks and volumes and everything. Doing a stack RM is gonna clear down what's defined in the YAML file. Okay, so let's clear this down and get rid of my terminal. So this is really simple, but exactly what I've said there. I could be describing dozens of services in my YAML file, and I manage it all as a single stack. So it's a nice kind of way of dealing with a distributed application that ultimately defines a single part of your business, and you're working with it as a stack. Okay, cool. And this is the big difference between Compose and a real orchestrator is that I can manage those resources without the Compose file. So when I was doing the service list, when I was doing that. I could do like service logs and all those sorts of things. I don't need the YAML file locally. So all the things I do with Docker Compose, I have to have the Compose YAML file, so that Compose is a command line tool. It can look at the YAML file and then work out what's going on inside the Docker engine. I don't need any of that stuff when I'm working in an orchestrator, because the application model is stored inside the cluster database. So as long as I can connect, I can work with whatever's deployed. Okay, so that's the kind of basics. I've got my YAML definition. I've got some bits of the container environment that I can set up there. And then the next thing I can do is, when I'm looking at production, obviously I've got a different application configuration to apply. And previously, we've done that with lots of different techniques. We've used like a default configuration baked into the container image. I've got a picture for this here. So if I'm running it in the dev environment, I'm just going to I can do a Docker container run or a Docker compose up, and it will just work without me having to plug in a bunch of environment variables or other ways of defining application configuration, because the default environment is set up for dev. And then in the test environment, I'm going to use some other things. So I'm maybe going to use compose again, but I'm going to use environment variables. I'm going to use secrets, which are just local files, to inject the configuration into that same Docker image. So I've talked this like over and over again, that the goal is to have a single image that you promote through your environments. So I've got my application image, and then I'm applying the app configuration from the platform. So in Compose, I'm going to use all the techniques we saw, like environment files, environment variables, and then external files. But when I'm in production, I've got these first class objects. So a config object is a concrete thing that you create inside the cluster, and a secret is something similar. So you can create these config objects, and then in your application model, you effectively, kind of like a bind mount. So here's the source is my config object, and the target is the location, the path inside the container where that config object gets deployed. Same concept with Kubernetes. So I can create config maps in Kubernetes. I can create secrets, and then in my modeling, I surface them inside my container. The container still needs, the application in the container still needs the logic to know that it should be going to this particular path to find a config file, and then it should merge in the config file A and config file B and a bunch of environment variables. Your apps need that logic in them to be able to source config from different places, and then your orchestrator, your container platform, can provide the correct config for the environment. Okay, and we're going to see that in action now. So I've got a config object to deploy. So no, not that one, that one. So I've got a config object here. This to-do application is a .NET application. All the demo apps that I use in the book are all sorts of different languages. So you can kind of play around. There's Go, there's Java, there's a bunch of different things. Node.js. This is the kind of configuration model for .NET Core, which is the cross-platform .NET environment. It's a JSON file, and it's kind of just a hierarchical structure. So I've got some logging levels set. I've got a database provider. So I talked about the to-do application. It can either run with a local SQL-like database where the file lives inside the container, or it can connect to a remote database, which might be another container, or it might be like a managed Postgres service, whatever the deployment environment has. This configuration setting tells it that I'm using Postgres, so it's going to try and find my Postgres connection and access that as the database. Okay, so the way I manage that is I create that config object from that file. So I can do a docker config create. I give the config object a name, so I'm calling this to-do list config, and then the path to the source file. So this is JSON. It could be XML. It could be like a Java properties file. It could be just key value pairs. It could be whatever. YAML, TOML, anything like. As far as the cluster is concerned, it's just a file. It can even be a binary file, and inside the container it gets surfaced, and the application needs to kind of know how to read it. So I create my config object, and config objects are a real thing. So I can do a docker config ls. That will show me I've got my config object, my to-do list config. It's been there for 6 seconds, and now I can work with that in my application definition. What I get here is because it's stored in the swarm, even binary files there, because it's stored inside the cluster of the swarm. So if I had multiple managers, it would be shared in that kind of distributed database that the managers all have. So the state is the same for all of them. If I declare inside my application model that I need this config object, then whichever server is gonna be running that container, the manager provides the content of that config object, and then the server can surface that inside the container at the desired location. So the config objects, they all live inside the cluster, but they get provided to whichever server is going to run the container that needs it in the spec. Okay, so we can go and look at the contents of that config object. So the only real difference between config and secret is that the API is very similar. I do a Docker config create, a Docker secret create. I provide it the source of the configuration. The big difference is the config is not meant for sensitive data. So when I do a config inspect, if I pass the pretty flag, I get the raw data back out. So I can see the contents of the JSON that I uploaded. I don't need any special kind of privileges or permissions to do that. As long as I can connect to the API manager, to the Swarm manager, I can look at the config objects that are there and I can read out the data that's in them. So what gets stored is this, along with a bunch of metadata, so like the name and the created date and all that sort of stuff. But it's not secure. It's just stored in plain text. It's delivered in plain text, and anyone who's got access to the cluster can go and look at the details. Now, the reason that this is useful to separate the config object from the application model is that often they are managed separately. So depending on, there are lots of different ways to do this stuff, but often there's a configuration management team who own the config, whether it's sensitive or not, and they will apply it in the environments, or they'll get involved with the packaging. So there's a final kind of production package that has everything you need. The workflow when you're looking at an orchestrator is either whoever owns the config, whether it's a separate team or whether it's the product team, they will deploy the config objects first and then deploy the application model that uses those config objects. So what you get is a kind of two-step workflow, which says, like, here's the new config that I'm applying, and here's the application model that uses that config. So that lets you kind of separate out the responsibilities, which matches the way a lot of people do things, and it just means you can kind of clearly separate. The config can be created in advance by a separate team. The secrets can be deployed by a team who have access to that sensitive data, and then the DevOps team or whoever, the product team, can deploy the application without knowing the contents of the config in advance. So the YAML file that describes your application lives inside source code, but the config and the secrets can live somewhere completely separate that is owned by and permissioned independently of your source code. Okay, so this is what this looks like from the application point of view. So let's go and look at this for real. This is version 3. Yes. Okay, so in version 3 here, there's a couple of other things. So firstly, I've got my config setting in here. So this is saying, again, this is part of my compose specification. It's saying the source is to-do list config, which is just the name of the config object inside the compose spec, and the target is /app/config/config.json. And that's the bit that the application needs to know about. So this will get surfaced, the content of the config object that I've deployed in my cluster, that will get surfaced inside the container at that path. And then it's down to my application to know that I need to look in that path. And then the contents of that file will override the defaults that are baked into the image. Okay, I've got another complete entire new service in here. So because I'm running with Postgres this time, I've got an additional service which is going to run my database. So I've got a single replica for this. I've got some slightly more generous limits. It doesn't use a lot of CPU, but I've given it some more memory because it's a database server. A single replica, so that's going to run in the same cluster. It could be on a separate machine, but the same networking abstraction works for Docker Swarm as Docker Compose and ordinary Docker containers. The to-do-db becomes the DNS name of the database server. So inside the connection string for the web application, this is how it's going to find the database. Okay, there's another top level section here. So there's a config section that says this to-do list -config is external. Like, it already needs to be created in the cluster, and the Swarm isn't going to manage it itself. It's going to need to be already created for this to work. Okay, so let's go and deploy this. I assume that's what we're doing now. Okay, yes, there's a whole bunch of things in here, which is just what I've said. I'm going to open up my terminal and deploy this. And this version of the application doesn't actually work because there's not enough detail in the configuration model so far. I've created this config object that tells the application to use Postgres, but I haven't yet given it a connection string, so it doesn't know where to find the Postgres database. But it's all up and running, so there's no kind of good health check stuff in here. So this is the situation when I talked about adding reliability with health checks and dependency checks. This is the situation where I've got a false positive. Everything looks good. Right, so I've got my web database there for my to-do list application. and I've got the web instance itself. I've scaled down to a single replica to make it easier to work with. It looks fine, right? I've got 1 out of 1. It's not restarting. It's all looking good, but the application doesn't work. If I go and browse to 8080 now, let's go and get this here. I get this nice white screen, which kind of tells me that something's not quite right. And if I go and look at my services, so if I do service list, my to-do dash web, oh, sorry, Billy, double click. Let me have a look at that. If I do a Docker service logs, I'll see like a massive ton of logs. And if I scroll all the way up here, it would say something about not being able to connect to Postgres because the connection string hasn't been provided. So somewhere here, there we are, something to do with Postgres. Okay, and I know what that is because I haven't given it the connection string to talk to the database. I've told it in the application configuration, which is non-sensitive, so that lives in the config object. I've told it to use Postgres, but there is no connection string, so it doesn't know where to find it. Okay, so when you run that, when I did the Kubernetes book, anything that I expected, any exercise that I expect to fail, there's a comment in there saying this will not work in case you're skimming through. And if there's a second edition of this book, I would go and write those things in there so you don't get confused, which is exactly what I did when I ran through the exercises earlier. I was like, oh no, it doesn't work. But it shouldn't work. So that's what it says in here. The config object tells it to use Postgres, but it doesn't provide the connection details. So we'll fix that next. Now, this is the connection details are likely to be sensitive. So depending on how your database connections work, the simplest way, there's going to be a username and a password inside my connection string that my application will use to authenticate with the database so it can read and write data. So that's sensitive stuff. That should not live in a config object because, as we've seen, anyone with access can do a Docker config inspect and see the whole contents out. So when we're talking about sensitive data, we're talking about things like usernames, passwords, URLs for production services, API keys. Anything that you're not sure about, then you kind of run that past your security team because even things like cache sizes might potentially be considered to be sensitive because if someone can read that, they can kind of maybe infer that if they bust that cache, then something interesting might happen. So your idea of confidential might be different from your config management team. So always worth kind of checking what they think is sensitive. Okay. Now, the sensitive part, the API is exactly the same. The command is the same, Docker secret create. So in this case, I'm going to be creating this secret here. And again, the format Docker doesn't care about. So this is another JSON file. This will get surfaced inside the container to a different file path. And again, my application is configured to read both those paths and merge all the contents together with the default that's baked into the image. And ultimately, you'll get this kind of production deployment. So inside here, I've got my connection string. The server is TodoDB, which is the name of the service inside my compose file. The user ID is Postgres, and the password is Postgres. So you can see that's sensitive, and it's it's obviously a really good password to use. So the way I work with this is I just do a Docker secret create. So I'm going to point it to that JSON file that we've just looked at. That's the source of the secret, and it's going to create this thing called to-do list secret. So again, first class object, I do it with a Docker secret command is how I manage it, and I'm going to do by create. And I can do a Docker secret inspect. I can do a secret list and a secret RM and all the same kind of standard verbs. The difference is this is the same as when I did the config inspect with the pretty flag, but I don't see the contents of the secret, and I can't ever see the contents of the secret. So the secrets inside the Docker Swarm database, the cluster database, are encrypted. The communication between all the nodes inside the cluster is encrypted anyway. It's all encrypted with TLS. So as the secret moves from the manager to the node that's going to run the machine, it's encrypted in transit. And then in Linux containers, the secret is surfaced inside like a RAM drive. So it's not written to disk in plain text anywhere in that kind of whole workflow. So that's all just when we did that Docker Swarm init with a single command to create the Docker Swarm cluster. All that whole mechanism just gets provided by that. So the secret management is one of the strongest points. It's just so super easy, but you get this really secure workflow all the way through from the secret that lives encrypted in the database to being surfaced inside the container. The only place you can read it in plain text is inside the container, which doesn't mean that it's completely bulletproof, but it does mean that it's difficult to intercept it in between there. Okay, so this is the stuff that I'm talking about here. The compose syntax to use that secret is very similar to the config list. So when I have my config, the source was to-do list config, and that's the target path inside the container. And it's the same with secrets. The source, that's where am I getting this secret from inside the cluster, and then the target is app config secrets. So we use secrets in Docker Compose, but it was kind of fake. So we use secrets to take a local JSON file and inject it inside the container. This isn't fake. This is really is a secret. It lives inside the cluster, and it's encrypted, and it has all those semantics to secure it as it moves around. Okay, so we can deploy this now. So I'm on version 4 of my YAML file. How are we doing? We're just over halfway through. I think there's only a couple more to do. So I get two reports out that it's updating the web service and it's updating the database service. You always get that when you do a stack deploy. The desired state thing happens inside the cluster, and the communication between the command line and the cluster just says, like, effectively, I don't know what I'm going to do yet, so I'll go and update those things for you. But actually, it doesn't make any change to the database component because I haven't changed the definition. So if we go and look at the replicas for the stack, so these are all the containers that make up all the services in my application. What I'll see is my to-do list database. It's been running for 6 minutes, so it's the same container, even though the command looked like it was updating it, which you might infer is going to replace the container. It's the same container. Here's the web one that got replaced 26 seconds ago when I deployed my new definition. And again, any kind of significant changes are going to result in a new container. So I didn't change my database definition, same container. I changed my web service definition to add in my secret. And again, that's part of the container environment that's created when you create the container, and it lives for the duration of the container. So I can't edit an existing container to add in that path. It's kill the old container, start a new one. So you need to get used to the idea that updates are all about throwing away your old container and starting a new one, and everything's kind of built around the fact that that needs to be safe. Okay, so now that's done, what I should find is that now it actually works correctly. So if I go and browse to port 8080 this time, now my web application container is connecting to my Postgres container because it's got access to the secret, which contains the connection string. So we can go and look at that connection string, and it knows how to connect to Postgres. The Postgres database image is built with that username and password baked in as the default. But of course, if I was doing this properly, I would pass a secret into the Postgres database as well. So I'd have a secret that said, like, here's my Postgres username and password, and I would apply that to the Postgres service, and then that would match what I'm applying in my application configuration in my application secret. So I haven't done that for this, but you get the idea. The hard-coded stuff inside a Docker image, bad idea. Managing secrets inside your orchestrator, better idea. Okay. So if I have a look at this view here, now this is what it looks like so far. So I've covered kind of most of the main pieces of orchestration so far, apart from state, which we will look at shortly. So I've got my application container here. It's got secrets and configs. They live inside the cluster. They're managed by whoever's managing the application, but separately from the application model itself, and accesses those to configure the application and give it the access to sensitive data to tell it to find other services. And then I've got my ingress component here. So there's the published port on the whole cluster. That's cluster wide. Any server on that any node in my cluster can receive traffic and forward it to the right container. And the thing that's missing so far, which we'll get onto now, is state. So right now, my database container is just storing data files locally. So it's not using a kind of volume that I can manage independently. And when we talked about state way back in week 1, we talked about having a Docker volume as an independent life cycle from a container. So if I want to be able to do things like update an application image, update to a new version of my application, to a new image, without losing the data, then my container needs to have the data separate from its own lifecycle. So my V1 container writes to a volume. When I deploy the V2 image, it kills the V1 container. The V2 container starts up, connects to the same volume, and it can see all that state. And you can affect the same thing with volumes inside your cluster. Okay, so let's go and scroll down here. So here's the kind of workflow that I talked about there. If you are having separate teams that manage configuration, or if you manage it all within the product team, the workflow is always going to be when you do a deployment, you create a new config object or a secret. You update the name of the secret or the config object that you're using inside your YAML file, and you do a deployment of your stack. So that means even if I want to change config, I'm effectively going to end up replacing containers. There are different semantics for different applications that work in different ways. So applications might have a watch on the file that contains their configuration, And if that file changes, they can do like a hot reload. So the application process doesn't restart when there's a configuration image. But that isn't really supported in Docker Swarm, because if it's a change to the config, you're always going to get a change to the container definition, and that will be a replacement container. Kubernetes is slightly different. Kubernetes lets you choose whether you want to update existing configuration or replace and restart. But unless you're certain that your app can deal with kind of hot reloads of configuration files, it's kind of good to assume that any change to config is going to be a new container anyway. So Docker Swarm kind of forces you to do that, but you might need to accept that that might be what happens anyway, unless your app is specifically configured to allow hot reload. So an update to the secret inside the cluster in Kubernetes, you can update an existing secret and that gets filtered out to any containers that are using it. So the file content on the container file system changes, but that doesn't mean your app is going to notice that and reload itself. So you need to fully understand if your application supports it, if you want to do hot reloads. Okay, so yeah, update services shouldn't scare you. So you should be expecting that you're going to do lots of updates, because that's the beauty of having a dynamic container orchestrator, is you can do safe updates. You can just throw your new definition at the cluster, and it will start everything that it needs to start. Okay, cool. So now I'm going to move on to volumes. So we covered Docker volumes what seems like a long time ago. They're this kind of unit of storage that's separate from the container. They're the same in orchestrators too, but there's a kind of big difference in the type of the volume. So when we looked at volumes in chapter 6, which would have been episode 5 of the stream, we looked at local volumes. So they live on the disk. I can do a Docker volume create, and it effectively just puts a name around a folder on my server or on my desktop or whatever. And so when I mount that volume inside my container, the container writes to whatever path it's mounted to, but it really gets stored on that folder on my disk, which I can reference as a volume. When you're running an orchestrator, it's more complicated than that, because none of the orchestrators kind of replicates volumes between all their servers for you, because that would be like an unknowably complex undertaking, given that you might be storing gigabytes and gigabytes of data. So there are different types of volume driver. So if I'm running locally by default, if I schedule a container to run on a node, so the manager says, right, this container is going to run on this particular node, and that service is defined to use a volume, it will use a local volume on that node. So the data will be stored in a volume on that node. If I kill the container and start a replacement container, if it's on the same node, it will access the same volume. If it starts on a different node, there won't be a volume, and it'll create a new one. So you need to understand that volumes are not replicated around the cluster unless you use a shared storage component. So local volumes are fine for things like temporary data that it doesn't really matter whether it's there or not. So if your application caches responses from some other API or from some database, because it's quicker to read from the cache on a local file, and then a container starts that doesn't have any cache, the application still works. It's just slower while it fills up the cache. So a local volume is fine for that. For anything where you really need persistent state, then you need like a plugin that says, I'm running my Swarm in Azure, and I'm going to use Azure files as my storage driver. So when I create a volume, it creates a shared storage component. In the data center, all the big kind of clunky storage devices have volume drivers, so you can use those as shared storage components. Okay, so the way to get around to the other way to get around the fact that you might not have a shared storage component and you're happy to restrict where your containers run is that you say, look, here's where the container will always run on this particular node or one of these nodes. And so that when the container gets scheduled to run, it will always be on this particular node. So as long as that server is up and running, that's where the volume will always be. So container 1 starts on node 1. It gets updated for a new release, and it starts on node 1 as well, because it's kind of pinned to a specific node. The way you do that is with labels. So I can do a Docker label apply. So let's say I've got a server in my cluster that's got it's got a RAID array, like super reliable disk. I want my database container to run on that server. I can do a Docker node update to add a label. Labels, talked about them before. They're just kind of arbitrary key value pairs that you use in your management of Docker objects, whether it be containers or volumes or networks or nodes in this case. And I'm adding a label with the key storage and the value RAID, and I'm just grabbing the ID of my first node. So I've only got one node, but if you were running with multiple, it would add a label to the first node. Sorry, to every node. I've only got one, so that's why I'm only getting one. Okay, so I've added that label in there. If I do a docker node inspect, and again, if I pipe in this command here, that will give me my node ID. Again, I'm going to get a whole bunch of JSON coming out because the inspect command is the same everywhere. I've got things like the manager status. I've got the TLS certificate for the root authority that gets created. I've got all the different plugins that are provided, which includes things like log drivers, volume drivers, and network drivers. And way up here, I've got the platform and the architecture. I've got the number of nano CPUs that it's got available. And way up here, I've got the label that I added. So this was my custom label that this has this saying that this node has RAID storage. So I can use that in my application definitions to say I only want to run this container or only want to run containers for this service on a node that has that label. And you'll use that in different ways. You can say, I only want these services to run on manager nodes because they are. I know that they're a highly available set, or I only want them to run on worker nodes and not manager nodes, so the managers can be left to do managing stuff. Any labels that you want to apply, you can use them in this way, and that comes in the deployment constraints in here. So let me show you the v5 file. So again, it's an extension of what we've had so far. So my services, you see the YAML is just getting bigger and bigger and bigger as I'm adding more and more kind of production-y stuff to my application model. And that is exactly the process you will go through. You'll go through, here's our Docker Compose file that we're using in dev. It's nice and simple. The test environment, we want a couple of extra replicas in there. For our non-prod environment, we want to throw in those resource limits. And then we're also going to obviously add in our database. We're going to put in it just grows and grows with the requirements that you need for each successive environment. Ordinarily, you would have your override files and all that sort of stuff. But to keep things simple for the demos here, I'm just putting them all in one big YAML file. So the new difference in here is I have got defined inside my database service definition. I've got a volume defined, which is saying that I'm expecting to use the source. Again, same kind of volume specification that you use in Docker Compose. The source is a volume called to do DB data, and the target is this folder here, which is varlib Postgres SQL data. And then to make sure that Postgres uses that data, that location to store its data, I've got an environment variable. And again, that's something that's part of the Postgres Docker image. If that environment variable exists, then it reads that as configuration, and that's where it stores its data. And the other thing I've got here, again, in the deploy section, so this only applies in swarm mode, is this placement constraint that says the node label storage has to exist and it has to have the value RAID for any containers to run on from this service on that node. So when you throw this application definition into your cluster, the scheduler, which is the bit that works out which servers are going to run the containers, will use this as a hard constraint. And if I remove this label from my node, this service would never run because there are no nodes in my cluster that satisfy the constraint. Okay, so let's go back and deploy that now. So I'm going to go and clear this down. I'm going to look at the volumes I've got right now, which may or may not be a bunch of stuff. Yeah, so I've got a bunch of volumes in here. Oh, this is the one I created earlier. I'm going to remove that when I ran through my demo. So I'm going to do docker volume rm. So just pretend this is the bit I would edit out if I had the editing opportunity. So I'm just going to do docker volume ls here, which will list all the volumes, and they're just kind of random IDs. So again, going back to episode 5, which is chapter 6 of the book, volume, you can put the volume instruction inside a Docker image, which is like a kind of hint to users that data needs to persist between containers. And when you run a container from an image that's got a volume instruction in there, it will create a random volume. So that's what I've got here, a bunch of random volumes. If I run this without the Q flag, we will see these are all local volume drivers, so they're all just local disk. If I was running in a cloud environment, I would use the cloud driver. If I was running it in on-prem environment in the data center, I might have my own storage unit would have its own driver. Okay, so now do a stack update. So this is a fairly significant change because it adds in all the volumes and stuff, and it adds in my replacement definition for my database. So this will replace my database container because adding the volume again changes the container environment. So that's a new container. So if I now look at my volumes again, and incidentally, if you're using Windows containers, there's slightly different here. So again, because of the paths, you can't kind of neatly model a generic file path at the moment with your compose files or your stack files. So that's why there's a separate one for Windows. And here, look, there you are. I've got my my volume called to do db data. So the cluster created that on the node that was scheduled to run the container, which is the only node I've got, which is the one that has my label applied. So the container will always run on the node that has this label applied, and so a replacement for my new database container will be able to use the same volume. So that's because it's a volume that's inside my compose definition is managed for me by the swarm. It creates the volume of the correct driver, and it leaves it up and running there. Okay, so the one thing that Docker Stack RM doesn't do is it's not going to remove my volumes for the same reason that there could be a bunch of important data in there. So I'd have to explicitly remove it, as I did at the start when I realized it shouldn't be there with Docker volume RM. Okay, so here we go. So the volume has the same lifetime as the stack. What I can do now is if I do a Docker Stack deploy. Oh no, I need to write some data to show you how this works. So this is my application. It's up and running now. It's still using the Postgres database container, but now that's a new Postgres container which is using the volume. So if I go and add a new thing to plan episode 13, there's my list. I've got one item in the list. I go and look at the list, and there it is there. Okay, so now if I do an update, and what this does on my v6, how are we doing? 9 minutes. If I look at my v6 YAML file, the big difference here is the to-do image. So this is a database upgrade. So I've got a new version of Postgres that I want to run. So obviously that's going to be a new container because it's using a new container image, but the setup is the same. So the environment is the same. So it's going to the new version of Postgres, when the database server starts, it will look in this folder for its database files, and that folder is being mapped from the volume, which is called to do db data. And because the placement constraint is the same, so let's go way down here. The placement constraint is the same. It will run on the same node, even if I had like 10 nodes in my machine. If there was only one of them that matched that constraint, so it will run on that node. That volume already exists on that node, and so the data will still be there. Okay, so back here, no, not that, this and this, and I'm going to do a Docker Stack deploy. So it's always the same command that I'm running. The number of the file changes because I'm doing it in this way rather than progressing through time. But that updates my web and my service. It doesn't really update the the web service because there isn't much to do there. Same definition. If I go into a stack PS, obviously all these things here that describe what I've been doing since the episode started. So I've got my to do DB that was shut down 2 minutes ago when I did the first deployment with the volume definition. I've got my to do DB that was shut down 12 seconds ago when I did my upgrade from 11.5 to 11.6. And if I make this a little bit bigger, we'll actually be able to see the image name. So the one that's running now is 11.6. Been running for 12 seconds. The one it replaced was 11.5. So this is 11.6 probably has an updated version of the base operating system as well with a bunch of patches, an update to my database server with a bunch of patches. So I'm not changing my application, but my application doesn't exist in isolation, so I need to keep my dependencies up to date too. If I clear this down and look at the volumes again, I will find that my to-do DB data is still the same volume, so that same volume is still there. So if I refresh this, it's all still there. So my data is still there. So I've survived a database upgrade. The data hasn't moved on. The data hasn't been replaced than when the container started. And again, this logic needs to live in your application. So if you've got a stateful application, when it starts up, it needs to go and read the data from a location. And as long as you can configure that location, then the data will live in a volume in between your container restarts. Okay, so we've seen a whole bunch of stuff there. So we've seen config and secrets, and we've seen how to define your stack in a YAML file. We've seen placement constraints and resource limits and all that sort of stuff. And it's really just all extensions of what you're putting into your YAML file. Your YAML file models your entire application. You can put your storage in there, your configuration in there, and your network in there, and everything just kind of gets put together for you and managed by the swarm. Okay, so how are we going down here? Yeah, so this is the bit that I was talking about. When I did my Docker info command and it listed all the plugins, I had plugins for different logging drivers, different network drivers. I only have one plugin for my volume driver, which is the local volume driver. But this is the part that allows you to plug in different providers for your storage, which could be distributed storage that any server can access. Kubernetes has a similar model. And there's this movement called CSI, the Container Storage Interface, and hopefully Docker Swarm will have support for that. That's one of the things that's planned for Docker Swarm. So you'll be able to say, if you're a storage vendor, you create a driver that matches the CSI, that works to the CSI specification, and then people can use that in Kubernetes or Swarm or whatever else supports CSI. Okay, cool. So this is the part here. So I've got all these components that are defined in YAML, and the Swarm is managing that stack for me. There's a couple of things here. Volumes can be created and removed by the Swarm. I'm not sure that's true, so I'm gonna double check that. I'm hoping the book is right and I'm wrong. If I do a Docker stack ls inside here, and I do a Docker stack rm to do. Okay, so it removes. Yeah, so it doesn't remove the volume. So Docker volume ls. Yes, my volume is still there. So there's a this is wrong in the book. Don't tell anyone from Manning. So volumes can be created and removed by the Storm. Stacks will create a default volume if specified that will be removed when the stack is removed. So that's not true. Not true. So it does not get removed because Docker doesn't remove volumes and stuff unless it's sure that you want them removed. So if you specify a named volume, hang on. Oh, it's okay. It's okay. If you specify a named volume for the stack, it will be created when you deploy, but it won't be removed when you delete the stack. So that's why. If I just specified a volume, but I hadn't given it a name, so it was just a random volume, then it wouldn't be removed. But this, because I named it, it doesn't get deleted. I don't need to rewrite this chapter. Okay, so secrets and configs are created with the external file gets uploaded. So there's that different workflow. I create my config objects and my secrets object, and then I reference them in my model, in my YAML file. And so I can split the responsibilities if I want to. They can't be updated. So a new config is a new deployment of your services. So if you're using Swarm, bear that in mind. If you're using Kubernetes, that isn't true for every circumstance, but the number of bits in the way of a hot reload are significant. So you need to make sure that that whole workflow works if you're expecting to be able to do just an update of an existing config object. So networks can be managed independently. Every site will be deployed with a network to attach services to. So even if you don't have a network block in your compose file, the Docker Swarm will create a network for you and plug the containers in there in the assumption that you are going to want to connect things through. And then services created and removed when the stacks are deployed. So this section is just telling you that what are the life cycle of these things. Swarm is going to monitor your stacks and make sure that the service level is always up. So the number of replicas you specify, Docker will do its best to make sure you always get that number of replicas. So it'll start replacements. If things are unhealthy, it might remove them and replace them and all that sort of stuff. And if a node goes offline, as long as there's capacity, it will start as many replacements as it needs to. It's not always true, depending on things like your CPU limits and requests. You can request a minimum amount of CPU in your deployment configuration, and if there isn't enough space left in your cluster when a machine goes down, you might not be able to get the desired replica count up, but it will do its best to try and get you there. Okay, so this is the way. This is the whole idea of the self-healing app bit. So the stuff we talked about in the previous episode about health checks and reliability checks, they really come into their own when you're in an orchestrator environment because it can take corrective action if things go wrong. And then lastly, there's the lab. So the lab is the idea to try and get you more experience with the YAML modeling process. So what it does is it asks you to take that NASA image of the day application that we've used so far in the series and write your own YAML for it and deploy it to Docker Swarm. So there's a fair amount of work to do there, but when I say fair amount, hopefully it's just looking at the YAML files from the exercises and using that as a starting point. So we're talking. We're not talking more than 30 minutes work, I would hope. And if you've gone beyond that, then here's the answer, which is up on GitHub. Okay, so how are we doing? So we've got a couple of questions here. So what's the advantage of describing a secret or a network external versus in the compose file? It depends on how you want to manage them. So if I've got, when I create a network, there are all sorts of interesting things that I can put into that network configuration. So things like the IP address range, the network driver. If I'm using, there are different drivers that I can use for different networking topologies. Maybe I've got a separate team who manage that stuff for me. So, as the application modeler, as part of the product team, I don't know anything about that stuff. Someone just tells me to use a specific network and I define it as external, and then my stack won't deploy if that network doesn't exist. So it gives me two things. It lets me separate the ownership of those objects, so I can separate the responsibilities, and it also gives me a nice kind of safety check. So if someone should have created that network and I flagged it as external, if I try to deploy and it isn't there, it won't create me a default network which might behave differently than we expect it to. It'll just not start. Same with secrets, like it just separates that management responsibility, so you can do things in whatever workflow kind of works for you. Okay, let's just Slack here. Okay, we're all good. So cool. So that was where are we now? Episode 12. Let me go back to my slides here. So that was episode 12. We looked at distributed applications. This was really all about the modeling language. So looking at how you use YAML, an extension of the Docker Compose format to specify all the extra bits of the configuration that makes sense when you're running in an orchestrator that can manage these applications for you. We looked at secrets and configs and volumes. So we've covered there's abstractions around app configuration and around storage and around networking, all with a really simple application you can go and kind of play around with. Tomorrow, what have we got coming up? Tomorrow, let me have a look, episode 13. We are looking at automating releases with upgrades and rollbacks. So I've talked about this, but this is all about making sure you do safe releases. So we're going to cover a whole bunch of stuff that all ties together the idea of the health checks and the reliability mechanism to make sure that your containers are healthy, and making sure that you tune your upgrade and your rollback process so that when you do an automated release, everything just works properly and it rolls out and makes sure that it's healthy along the way. And if there's a problem, it rolls back automatically. There's lots of things you can configure there, lots of tweaks, and kind of you need to have an understanding of what all the options are. And that's what we'll go through tomorrow. So thank you for joining. That's episode 13. We're coming to tomorrow. I hope you find that useful, and I hope to see you again. Thanks.